Good morning, Lindley. How you doing? Good morning, everyone. Come on in. Only 8 of us so far. I don't want to jump into anything. Sorry about it taking me like 5 minutes to get online. Don't know what was going on, but I was just waiting there somewhat patiently. I'm in the process of setting up what we're doing for lab today. I talked to you before about this. It's called a propagation of error. And of course, those of you who had me last semester, you've been through this before. But we also have people that weren't with me last semester that didn't get a chance to do it. So every student that comes through TCC is in physics anyways, is definitely getting a propagation of error lab. And eventually we're going to have it more robustly set up so that each lab has a propagation of error portion that students will make sure they get trained in. So I'm doing that little bit by little bit. So that's what this is about today, is making sure we all know how to propagate error as opposed to using the typical techniques of sig figs, which is really not correct. There's very good reasons why propagation of error, error propagation via sig figs doesn't work. So that's partly what this is about. You'll notice in week 11 of our course, there's a module week 11, October 31st to November 6th, and it has the Zoom invite, probably the one that you clicked on. Actually, it only has one, so it kind of worries me. I have to make sure I put up the other one. It also has Vernier. Oh, no, that's right. I put them both in the same document. It has a Vernier manual page, Vernier parts, and Vernier parts zoomed in. There's going to be more photos there as well. I'm just pulling them off the internet, off my email server now. They're kind of big, so you have to pull them down a few at a time. So what we're going to do is we're going to refresh your memory on how to use Vernier calipers. Of course, if you had me last semester, or if you had anybody at TCC last semester, you learned how to use the Vernier calipers and how to read them properly. So I'm doing the same thing in case you haven't. And even if you have, you probably don't remember that well. So it's better to have a second iteration at it. Does anybody have any questions or anything they'd like to ask me about before we get started?
Is this like the lab we did 3 weeks ago with the relative error? Yeah.
Yes. Yes, but it's a reiteration of it, specifically so we can handle some more specific things that we hadn't discussed before. In other words, go a little deeper. Of course, I'm going to review what we did as well, but I'm also going to, review it quickly as opposed to so minutely and stuff like that, like we did in the previous semester or the previous version. And like I said, I also have this portion about the Vernier calipers that we're going to make use of. Anybody else? I'm sorry I can't meet you guys today, and hopefully everybody got this message. Go ahead. Yes.
For the lab, the optics lab.
Yes.
I don't see a place where.
Thank you. You just reminded me of that. Yeah, okay. Ryan told me the other day. I'm going to put that up right now while you guys are talking to me, and that was in week 9, technically, if I remember correctly. Yeah, yeah. I made it. I think I didn't publish it. Let's see. Appreciate that. And that was. We call it lab 7, I think. Okay, there's now a spot there. I just got to make sure it has all of the technical aspects. It's kind of weird. You have to make it as just the name, and then after you make it, you have to go back and click on it again and make it have the ability to turn stuff in. I can write messages in there. I can attach documents, all that kind of weird stuff. You got to assign what kind of document it is or what kind of assignment it is. So this, of course, is lab reports. And you got to make sure it's submission online, file upload, and you got to restrict it to type PDF. And I did not put a due date on there. So actually, I'm going to put it now. And what it's going to be is 11:59 this evening. That way, anybody that hasn't turned it in obviously has the rest of the day to do it. And if they turn it in later, then it's going to have to be late. And that's, you know, to be fair to all you guys that actually had it done a week ago. All right, let me go back to my modules now. I'm going to share my screen in a second here. Let's do share screen. Trey wants my words in writing.
I think better in captions.
All right, so I'm going to share screen now, and let's see, I'm going to do this one. All right, so we're looking at our modules, and you'll see if you go down to week 11, obviously there's a lot of stuff I don't have turned on. That's because it didn't sync in the right semester as previous modules did. So here's this week's Zoom, October 31st. Happy Halloween, everybody, by the way. And you'll see the Vernier manual, Vernier parts, Vernier part zoomed. I've got a bunch of other photos I want you guys to be able to read. And that's probably the lion's share of today's meeting, is just to get used to that. And then I'm going to reiterate a formula and consider a couple other things. And this is the error propagation document that you've probably already done. Hopefully you've already done it and turned it in. No, I haven't graded yours. I graded the other classes. So I've been set back on that as well. So I'll get to more of that. But you see what's here now. What I want to go to first is look at this Vernier manual so I can help you with learning how to read a Vernier again. So this is kind of nice. It actually tells you how you're supposed to do it. So if you look, and we'll see the parts in a second, they'll make more sense, but y'all seen them all before, so that probably helps you. But if you see, this is the scale down here. So you look at this part, this is called the main beam, or the main, I think it's called the main beam. Yeah, that's called the main beam. And the numbers on it is on the sliding part is called the main scale. So if you see number 7, excuse me, actually I reversed those names. On the main beam, you see the main scale right down here. And you'll notice that if you count the number of spaces between 0 and 10, or 0 and 10 there, because it's 10 millimeters, which is the same thing as a centimeter, there's actually 10. So each one of those represents a single millimeter. If this was 0 and 1, as often happens, and in fact, I think ours is, yes, ours is in fact 0 to 1. That's why it caught me off guard. So you could sort of read this as 1.0, I guess. But if you look at ours, it'll read here, 0 here, and it'll read 1 here, not 1.0, but just 1. And there's 10 spaces in between these individual, well, this long line and this long line. Notice there's a shorter line dead center between them. That shorter line, of course, is the 5th one. So that way you don't have to always count, you know, from here all the way to here. You can just say, oh, well, here's 5. So the next one's 6 and then 7. So what you want to do when you're looking at that is when you're looking at any measuring device, you want to take the difference between one measurement and one measurement 1 unit larger and count the number of places, so you know what decimal place they're actually telling you. So in this case, if you're measuring something between 1 centimeter and say this scale goes up to 15 centimeters. Actually, it goes up to quite a bit higher, 16, just not marked, 16, 17, 18, 19. This goes up to 19 centimeters. So if you're measuring something between 0 centimeters and 19 centimeters, then what you could do is you first look at, say, 3 and 4, count the number of spaces between them, and you say, oh, there's 10. And of course, the 10th place is 1 decimal. So that tells you they've got marked 1 decimal. But all measuring devices, unless there's something wrong with the thing you're measuring or the way you're measuring it, all measuring devices allow you to estimate, because we're not morons. We don't see everything in base 10 or even binary. So we can obviously tell the difference between 1.00 and 1.09. I think y'all all agree on that. And we can probably tell the difference really easily between 1.00 and 1.5. So our error may be as big as 0.025 if that was the best we could do, but I don't think we're that bad either. We can probably tell the difference between 0.00 and 0.02, or excuse me, 0.00 and 0.02. I would say that's probably pretty reasonable, and that would be an uncertainty of half that distance, which is 0.01. So with just the main scale, you should be able to read to 2 decimal places. That's the way measurements make. If you're using a meter stick and it's marked to the nearest hundredths, and you're measuring in, or excuse me, to the nearest tenths, and you're measuring in centimeters, you should be able to measure down to the nearest tenth. Okay, what this Vernier scale does is actually allow you, in this case, unlike the other cheaper versions we have, in this case, you should be able to measure down to the nearest, not hundredths, but in fact, thousandths. And that's what a Vernier scale normally does. If you go to a machine shop, for instance, they'll have a Vernier scale that reads down to the thousandths of an inch. Anybody have any questions on that? And so the way you do this is, if you look on here, it has actual instructions. So once you figure out what those parts are, like you see number 1 is the claws that actually measured things. I call them claws, they're actually jaws. But anyways, if you're trying to measure, say, the inside diameter of a glass or a thimble or something like that, then those number 1 are very good for that. If you're trying to measure, say, the outside diameter of a glass or a nut or a bolt or something like that, which wouldn't be diameter in a nut, but anyways, you would use number 9 down there, which is called the outside measuring jaws. And then finally, if you want to measure the actual depth of a hole, you'd use number 4 down there or up there, which is called the depth bar. And you can see down in the drawings at the very bottom how they're supposed to be used. You can see the internal measurements, like the inside of a socket, for instance, or the inside of a tube, would be measured with the inside measuring jaws, like shown in the far left, or the middle left, or the middle as well. And then the outer ones, of course, are measured with the part number 9, and then it shows you the depth measurements measured as part number bottom left, say. Okay. You can also measure a step, which is kind of nice. So you can use the little collar area basically on number 9 to measure a step down or a step up, say, and that shows you what happens in the middle of the bottom. So hopefully that helps you better understand how to read the caliper, or better understand how to use the calipers. Now, in terms of actually reading them, you'll see, and let me show you for a second here. I'm going to stop sharing my screen just for a second. And I think I can share my camera. Not there. Maybe my camera's not on. It does not seem to be recognizing my camera. Not there, not there. This was working before, but all of a sudden it's not. Maybe this is it. No, that's not it either. It's a finder, it's calendar. Okay, so it's not letting me use that at all. Let's try another folder. Nope. Ah, there it is. Let's see. So second camera contact. I had to look under advanced. There you go. Okay, so you can see lots of calculations and all sorts of stuff like this. So this is a Vernier caliper, and another thing you measure, or you need to do when you first measure something, is you want to loosen the screw here. You want to find out what 0 is, what it looks like. So obviously, if this thing was closed, we should be measuring a measurement of 0. So you see a 0 right there on that scale, and you see it lines up perfectly with 0 on that scale. So that tells us something. That tells us that obviously, when we measure something, we're going to measure it to that little black line that connects to the 0 in the bottom sliding scale. So there's our sliding scale, sliding back and forth. And we're going to measure to that mark right there, the 0 on the sliding scale. And that'll give us our measurement of, say, 0.100, 0.200, 0.300, 0.400, 500, 600, 700, 800, 900, 1.000. Notice how I was reading everything with 3 decimal places. This Vernier caliper allows you 3 decimal places every time. Okay, the only time, like I said, you'd say the error is bigger than 0.001 is if there's some difficulty in measurement or there's some variability in the actual edge that you're trying to measure. Like if it wasn't a smooth edge, let's say, for instance, like this mauled up credit card that my dog got a hold of. So I'm trying to cover up numbers, obviously. If I was trying to measure the length of this, obviously there's some variability in where the edge is because my dog ate it, right? So that's a good example of an edge that's not clearly demarcated or indicated. So you can obviously say, okay, well, there's some uncertainty in this, and maybe it might be as big as 0.5 centimeter in that case, because that's how much my dog ate. But other than that, you'd say your instrumental error, and that's the important thing here, instrumental error is 0.001. If you had a hard time getting to it, so you had to look off, say, some distance to something, like you couldn't actually get to the edge here, and you couldn't actually get to the edge of this or something like that because that little rounded corners there. Well, that's another reason that maybe you might have to cite it, and of course the measurement wouldn't be that clear because you can't actually get to that corner without running over the other thing you're supposed to measure. So if you're just measuring this in, that would be a pain, or if you're measuring and it's beveled or something like that, that would be a pain. So that might actually, those types of things might actually cause your instrumental error to be a little bit bigger than a 1 in the last decimal place, but the standard idea is a 1 or 2 in the last decimal place. If something's on an electronic scale, then you'd use a 1 or 2 in the last decimal place that it shows you, and the manual will usually tell you what that is. So you can look in the manual or somewhere on the outside of the box, and I'll tell you what it is. So whatever you go to make a measurement, like I said, one of the first things you do is look at what scales you're using. This top scale we can see is actually in inches, and this bottom scale is in centimeters. And we can see that it goes from 0 to 1, and in that interval from 0 to 1, there's 10 spaces. That's the second thing you check. The third thing you check is what does 0 look like, so you can figure out how you're going to measure. So that's why where this sliding scale hits something, that's what we're reading to is the sliding 0. That's what we read to. That's not what we read the number as. We don't read the number off of that sliding scale, not yet. Okay. And then the next thing we do is we record the instrumental error. So whenever we grab a measuring device, the first thing we're going to do is look at what the units are, look at the number of spaces between 2 consecutive numbers, so we can know what decimal place it's in, look at how 0 is marked so we can know how to measure with it. And then we, of course, decide on the instrumental error. So we've always got to do that with measuring devices, period. And you should record that every time. And remember, each measurement's different. So, you might have one edge of a rectangle or a rectangular solid is perfectly smooth. So it has an uncertainty of 0.001 centimeters, but the other side's a little bit mangled because it was dropped or something, in which case that side might have an instrumental error of 0.002 or 0.003. So you just record that as for each measurement part you have to list the instrumental error. And the key thing about the instrumental error is, in addition to being something you got to find, that is the smallest error you can have for that particular measurement. So all the statistics stuff that I'm telling you about today, and we talked about in the past, all that statistics stuff goes out the window if the statistics gives back a calculation that has a smaller error than the instrumental error. You just have to throw the statistics that you did out. Not, literally, obviously you had to do the work, but you just can't use it for that particular measurement. Now, if the other measurement was gave you an uncertainty that was bigger than the instrumental, then you do keep that one, of course. So any questions on that stuff? All right, so let me stop sharing the screen. Okay, so we're back here and we've got our measuring device, of course, the Vernier caliper. And as we showed you, inner diameters for measuring here, obviously with those little inner jaws, outer diameter for measuring here. And of course, this is the step we talked about. So you can actually measure a step up to this little neck here, or you can just measure inner diameters. And this is supposed to be the most pristine part that has this little part there, but it is pretty well machined, so that has a nice edge there. And then, of course, we got this guy, which measures the depth of the hole from this edge down to the tip there. Okay. So that's our actual vernier caliper setup. Now I'm going to go back to sharing the screen of, there you go, the vernier caliper manual. So you see on the vernier caliper manual, and you guys can zoom this later. I'm going to try to zoom it now, though, just so we can get a little better view of it. Okay. So again, we're reading to the 0 on the sliding scale. And you see right here, this 0 is at, and notice this one's reading millimeters, but again, ours reads centimeters. So this would be 0.9 because this first number is 1, not 10. So we're reading this as 0.9. And they're reading it as or they're reading it as 9.0 basically, but they don't know what that 0 is. So they're just going to say 9 point. So you get your first number from where the 0 is. Now, here's the weird part. If you looked at these scales together, what you'd see is this 0 to 10 is actually longer than the 0 to 10 that's marked on the regular scale. So the vernier scale, what they do is they make it slightly bigger. Actually, that would really be a good time for me to show you this. Actually, I guess I can show you the other photo. Let me do that. Stop sharing here. Actually, I did want to share there. Sorry. I'll share that screen, but I want to close that picture and go back to another picture. So I can show you this on the camera, obviously, but I think it looks better in the photo that I took. So that's why I'm going to use that instead. So here's I think the part zoom would be better. I did not want to download that, but it looks like that's good. I don't have to cancel that. Okay, what I wanted you to see, and thankfully it's vertically oriented instead of horizontally, but anyways, I'm being facetious about that. You can see that this scale goes from 0 to a smudged out what would be 10. And notice the 0 starts at just under 1.1. Notice this ends at just after 6. Okay, what that tells you is that this is actually a little bit bigger scale, and you can sort of see that as well. It's harder to see there actually. So yeah, this photo is not the best thing. So let me turn the camera back on. Sorry about that, guys. I really expected that to be the better way. Advance, camera 2, share. So with it closed, it makes a little bit more sense. If it would ever hit share there. There we go. So with it closed, it makes a little bit more sense. But you see what they've done is they've taken sort of half the distance. Notice this is about equal to 5, but notice how it's a little different. We see that the zeros line up with each other, but what would be, in fact, 5 or 10 on the sliding scale is a little bit bigger than 4.90 on the large scale. So they've let me use the Simpsons word, they've embiggened it to 10, but then they cut it by less than a half. And what that means is now the individual marks, say from 0 to 0.1, is a little larger than 0 to 0.1 on the main scale. So what that means is, watch, when I pull this to the right, the first digit inside of the sliding scale, the first one of those lines that lines up with any line is going to be the 0.01. So watch this. Notice that just at 0.01, the first mark to the left of the 0 just hit. Let me see if I can zoom that a little bit. Just hit the 0.02 on the main scale. And the next one that hits will be the 0.03, or excuse me, 0.03, which is this guy right here. That's going to hit next when I move it just a little bit. and then the 4 head, as you can see already, and then the 1 head, as you can see. So what that does is by making it a little bit bigger than half the size, then it actually allows you to hit a next digit each time you go. So if you're trying to read 0.11, it's going to hit that second one a little quicker than it should hit the 0.12. That's the way the Vernier scale works. If you don't understand it, that's certainly understandable. It took me several years to make sense of it when I first saw one myself, but that's my attempt at showing you how this thing works. Is specifically they've altered the scale. First, they tried to measure something twice as large, i.e. they tried to measure 10. As you see, the sliding scale goes up to 10, but they fit it in an area slightly larger than 4.9, so not quite as big as 10. So by doing that, it's just makes it where one by one, sort of like on an odometer, one of these digits hits, then the next one, then the next one, then the next one, then the next one. And it's important to understand what these digits are, because when you go to read them, that is very important. So I'm going to use the end of this wrapper here and show you what these measurements are. So this is 0. That's helpful. My phone just rang, and because I have a Mac, it rings through everything. So if you read this, the sliding scale, now this is the one down at the bottom. Notice between the 0 and the 1, there's 1, 2, 3, 4, 5 spaces. So that means each one of these is 0.02. So this is 0.02, 0.04, 0.06, 0.08, and 0.10. 0.12, 0.14, 0.16, 0.18, and 0.200. Okay, notice 3 decimal places and all that. So that's how these numbers are read. And not only that, they don't have the individual digits marked, but you can still estimate them, as you're going to see with some other pictures I post later. There's a way that you can look at them and actually say, oh, well, it's not the 2 and it's not the 4, it's going to be the 3 between them. And usually what happens is you'll see one of these scale lines down here lines up pretty well with a arbitrary line above it. It really doesn't matter what lines on the main scale once you've got the first decimal place. It's going to line up pretty well, but the one right to the right of it will line up pretty well, and one will be to the left a little bit and the other one will be to the right a little bit. Then that tells you it's obviously got to be right in between those two, and therefore it's the odd digit as opposed to the 2 or the 4 to be the 3. Okay, so that's how that's read. So let me stop the share again, and let me go back to our screen share with the actual picture. Okay, so if you were to try to read this one, for instance, you can see I've gone past the 1.1. I'm almost to the 1.2, and it's not always obvious like it is here. It's not always obvious that I'm past that 1.2. We'll talk about that as well. But right now we're at past that 1.1, because we're on the main scale that has 0.1 as each unit. So it's not obvious all the time that we're to the left of, on, or to the right of the 1.1. In this case, it is obvious to me. And you see that that number would be called 1.0 something. Okay. Well, what is that something? Now what I do is I take these individual marks and I just look for one making a straight line, or just perfectly handshaking right here. See how all these are off just a little bit? That's just a little bit off. That's just a little bit off. We're looking for the one that's really, really, really pretty close to being dead on. Now you can see I'm really close to since it's to the left of, I'm really close to the 1.1. So I should be expecting like 0.09 or 0.08 or something. As you can tell, I took this photograph with the center of the camera being right over the 1, so we could focus on the 0 mark. That means I'm seeing parallax over at this end. So it's really hard to tell exactly what the right measurement is. But one of these lines, this one, 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 or some spot in between them are lining up somewhere, but because there's a difference in height between this edge up here and this edge down here, they look, even if they were right on each other, they would look separated, or they are spread by parallax. Okay, so you can't really read that there, but that's how you go about reading it. You first figure out what decimal place to one decimal place, what decimal place is the first decimal place. So in this case, we're actually past the 1, so we know it's 1 point something. And in this case, we're not quite past the 1.1, so we have to call it 1.1. And it stays 1.1 all the way up to 1.1. It doesn't matter if it's getting closer, or excuse me, it stays 1.0 all the way up to 1.1. It doesn't matter if it's getting closer to the 0 or closer to the 2 or what. Okay, what matters is what I'm past. And I'm sorry I said all that previous line talking about the 1.1 because I was misreading it, but this is 1.0 something. Okay, it doesn't become 1.01 until this line exactly hits that line, and then it stays 1.1 up until this line hits that line. So you always read what's the last digit it's past, not what's the digit it's closest to. Okay, so that's how we get our whole number, if there is one, plus 1 decimal place, is you find out where the 0 passes. So if the 0 is past 0.1, then it's obviously 0.1 something, no matter how close it is to the 2, unless it turns out to be exactly on. And in this case, the 0 is past the 1.0, but it's not 1.1 until this part touches that part. It doesn't there. You can see there's a little gray, so we know it's not that. Okay, so that hopefully shows you all. Now you can measure it with this device up in inches, and of course in this case it says thousandths of an inch. There's tenths, there's hundredths, there's a thousandths, so it can actually do that in inches, but we don't use the inch scale. So any questions on any of that?
So what would be the third digit here?
It's really hard to tell because of parallax, but let me show you how we can do that. I'll show you with the camera. So I'm going to stop this share and I'm going to do an advanced share with the camera. And we're going to try to read it. And I've actually used an entirely different measurement. So don't think we're going to get the exact same one. And you guys can take a screenshot, or you can just pause it and look at it up close. But you will be able to take a screenshot if you want, or you can pause it in real time to make a better estimate of this. So what we're going to try to do is I'm going to try to mimic that same measurement. So right now, I want you to realize this would be 0.5, because right now the 0 has hit the 5 or is making it beyond, right? So if I go just a little farther, it's still 0.5, 0.5, 0.5 up until right about there. Then you don't know if it's 0.5 or 0.6. It looks like it's a 0.5, but in fact, if you find that the only thing that lines up is this, then it is a 0.0500. If you find out the only thing that lines up is this, and it's 0.499 or 489. Okay, see how that lines up down there? So that one suggests, since the next digit is a big one, that suggests that it is in fact still slightly to the left of the 0.6. So we call that 0.598, because it looks like that lines up pretty well. See that's 91, 92, 94, 92, 94, 96, 98. If that 98 lines up, then that would be called 0.598. Now, with the one we were talking about, we had went past the 1.0, but not quite to the 1.1. So I'll say some measurement like this. So right now, I'm going to try to keep the camera perpendicular to the calipers so that we don't get parallax. You can see how that 0 moves left and right in the space between the 1.0 and the 1.1 as I tilt it different ways. So we're going to try to look straight on, but straight on from directly above the number. So right now I'm definitely realizing that's 1.0 something, because it's clear that it's that 0 on the sliding scale is nowhere near the 1.1. So we're definitely going to say this is 1.0. Now we're going to look by scrolling all along here and trying to find any number or any bar on the main scale making a straight line with whatever line on the sliding scale. So it doesn't look like the 0.02 or the 0.03 or the 0.04 or the 0.05 or any of those, or excuse me, the 0.02, the 0.04, the 0.06, the 0.08 or the 1.0 line up. But as you get to the fives, it looks like the, you know, the 0.052 is a little bit past a main scale number. The 0.54 is also a little bit past, but not quite as far. The 0.056 looks like it might be right on it, but you look a little closer and you realize, oh no, there's a little disconnect. And then you see the 0.058 looks pretty good, and the 0.060 looks pretty good. At that point, you look and try to look as close as you can. You could, you know, use a magnifying glass if you really wanted to. That would be sort of the smartest way to do it. But you look sort of now, not so much as if they're straight or not, because sometimes it helps to look this way. The lighting's not right, or it could help to look this way to try to see what they line up with. So sometimes that helps. When I look at the 5.8, which is just to the left of the 6, the 5.6, which is right on the 6, and the 6, or excuse me, the 0.6, not 5.6, stupid me. So when I look at the 0.058 and the 0.60, it's clear that the 0.60 looks a little better than the 0.58. But now it's not even clear if the 0.60 or the 0.62 is better. So this could be an instance where I would call that 0.61. You might call that 0.620. But that last 0, if you thought it was 0.62, that last 0 is important and you got to include it. So does everybody see what I'm talking about? The 0.60 versus the 0.620? Actually, it's just 0.62.
Yeah, because it looks like it matches the 0.58 and the 0.6 and the 0.62. They all look pretty good.
Close, don't they? Yeah. It's hard, and like I said, if it's even worse because we're not using, you know, this is not a flat lens. I'm not necessarily holding it perfectly perpendicular to the surface. Sometimes I find looking at this angle works better. Sometimes I find looking at this. Actually, lately I've been doing this because I realize how crappy my vision is. I've been getting really anal about, or obsessive, if you will, about being directly perpendicular to the surface and take a photograph of it, and then I zoom it in with my camera. And you can see on that scale exactly how close they line up. And that's what some of the photos will be when they're posted up here. So in this way, when I'm looking at this one right here, that really looks like 1.0. Now I'm feeling 0.62 again. In fact, now I'm feeling, but I might have moved it a little bit. So be careful with that. What we should have done first off is lock that down with just a little bit of tension, and then it won't move. But I may have moved it since then. And that might be why I'm getting subsequently different movement numbers, because, you know, I'm trying to hold it still, but I'm not necessarily perfect. So now it looks like 1.5, no, 1.060. Anybody disagree or at least understand how I wrote that? Or how I reached that conclusion? 1.0, because it's not quite to the 1, 1.0, and then I said 60, because it looks like that 6 lines up really perfectly with a line above, and the line above doesn't mean a darn thing once you get past the first decimal place. Okay, now the trick is, and this is the hardest part about these measurements, is when you actually get to something like like I was talking about before, let's say we're clear that that's past 1.3. Everybody can see that. As you get over to here, it's a little less obvious what's going on. So let me lock this down for a second. But let's use our logic a little bit. So this number is either to the left of the 4, in which case the next digit must be a 9 something, or it's just past the 4, in which case it would be 0.4 something very, very low. So you'd expect it to be 0, 0.2 or something like that. So that's what you look for when you have it really close to the lines. If I check on the 0 scale, it does to me look like 0.04 lines up pretty well. In which case I'd say this is 1.404. If I look down here and saw one of these lining up, in which case in which case I call it 1.398. But it doesn't look like the 9.8 or the 9.6 or the 9.4 or the 9.2 line up at all. So because the next digit's low, I know that it is indeed past the 1.4. So we'd call this one 1.4, and it looks to me like 1.440. And that's because of that 4 right there. The second one past the 0 makes a nearly perfectly straight line with the line above it. Any questions on that?
I need to see that. So you got the third digit. Okay, so I see that it's 1.40, and then you get you see that near the other mark, the second mark from the 0.
You're right. The sliding scale.
It looks straight with the, so that's how you get your 1.404. Okay.
Yeah, either it looks straight, or you can see that they're sort of physically touching each other and centered up. So when you look at it this way, it helps you see it looking straight. When you look at it this way and then you zoom in, it helps if you can see that the left edge is lined up with the left edge and the right edge is lined up with the right edge. When you get on that scale, it's a little easier to easier to tell whether that's so, but it's also a little easier to realize, oh wow, it's not that perfect after all. This one looks like it could even be the O2 might be closer. So you can see there's going to be some variation in the reading. If you actually are serious about every reading, you're going to vary on your reading from one measurement to the next. If you're doing it with another person, then they're going to vary in some reading from each other. And that's where the statistics comes in. So you're going to have 5 to 10 measurements, say, of each, let's say, width. And then you're going to take the mean of that 5 to 10 measurements, and that's going to give you your best estimate of the value that you're measuring for the width. And then you're going to take the standard deviation of that 5 to 10 measurements, which is summing up the difference between the mean and the individual value squared. And then once you take the sum of those squares, you're going to divide it by 5 minus 1 up to 10 minus 1, because it's the number of trials minus 1. And you're going to take the square root of it. That's the standard deviation. And that tells you that 65% of all experiments are going to have the exact same measurement for length, or plus or minus 1 standard deviation. And plus or minus 2 of those standard deviations would be 98%, and then the other one would be, or 95%, excuse me, something like that, 68, 95, 99.8, something. So anyways, that's what's going to happen. But what we use in science is not the standard deviation, but the standard error. So you're going to do the standard deviation of the mean, which is another name for it. And that means you're going to go through the same process, but you're going to imagine an infinite number of experiments, and you're going to take an infinite number of those experiments results and find out what their final results are. And basically 68% of those results are all going to be within one standard error of your results, and 95% is going to be within 2 standard errors, and 99.8% is going to be within 3 standard errors. So that's what you're going to put in the plus or minus after the mean. So the way you compute that standard error, though it sounds quite complicated, is actually easy. Once you have the standard deviation, you just divide the standard deviation by the square root of the number of trials, and that gives you your standard error. Okay. Now, when you're finished with that standard error, if that standard error is, let's say, 0.0009 or 0.0004, 0004, okay, notice that is smaller than the instrumental error of this device. This device can't give you any better. Best case scenario, it can give you 0.001. So if I got something smaller than 0.001, then I have to use the 0.001 for that length. Everybody got that?
Yes.
All right. Anybody have any questions on that? So that's with every individual measurement. That's not something you do when you take those measurements and calculate another quantity, because there's no such thing as that particular instrumental error, because you didn't measure that with an instrument. So only the individual measurements that you made can be thrown out, the statistics thrown out in lieu of the actual instrumental error, because you don't use an instrument, for instance, to measure volume. You don't use well, you can use, for instance, a graduated cylinder, but generally you don't have an instrument to measure volume or surface area or some other calculated formula. Okay. All right, so that's enough, I think, on the Vernier caliper. I'll put some photos up here.
So the instrument error would be 0.001.
At best, yes. For this, anytime I'm measuring with this device, the best it could be is 0.001. A lot of people might even argue it's 0.002, because you can see how much you and I, or even me and me, disagreed on a particular measurement. So that's why we sometimes have to say, well, I think the instrumental error is more like 0.02, or excuse me, 002. But yeah, it is always recorded to three decimal places. So even if you get a measurement, which is highly unlikely, of 1.00, you have to write that as 1.000. Any questions on that? So I'll post some more photos, and I'll probably post some photos with a question mark in the name, maybe, or something. That'll give you a chance to answer those. So what you're going to turn in this time for this lab is a couple of calculations I'm going to ask you to do. And then there's going to be a couple of Vernier caliper readings that I'm going to ask you to get. And that's all you're going to turn in. So let's go ahead and start the rest of this stuff. So I just noticed my iPad, which is what I was going to use, is not charged up. I don't know how. I thought I left it off last night, but evidently I left it on after I prepared. So let's stop sharing the screen right quick. And luckily I have this camera here. So I'm going to use that. And normally the camera is not nearly as good as the iPad, obviously, but I'll try to write big, and I think it'll work okay. So what I wanted to remind you about these error propagation is the fundamental formula and the quantities that we use. Those are the important things. And then I wanted to remind you that this works with, for instance, angles and all sorts of stuff like that. Oh, good. I got another pin here. So what I'm going to do now is I'm going to share the screen or with my camera, basically, and do in handwriting basically some of the basic understandings of what we're talking about. So remember, you're not going to use sig figs now to dictate the number of digits you're going to put down. Sig figs are really just a first order approximation, and serious science shouldn't generally be done that way. Okay. What you're going to do instead is you're going to, and this part's all in words, but luckily you are getting it transcribed. So what you're going to do is any measurement you're making with a Vernier caliper or a voltmeter or an ammeter or a galvanometer that you've made into an ammeter, is you're going to read the measurement to the number of digits that the measuring device allows you. And you're going to repeatedly do that several times, because there's always some kind of error that could be in there. There's some uncertainty. For instance, if you're measuring currents, there's some uncertainty in the current that's being supplied, you might have it recorded as 129.4 milliamps, but it probably varies between 129.4, 129.7, 129.3 or something. So that's going to vary. So each time you take a measurement, you're accounting for that. You're going to take, we've always said the bare minimum is 5, but to be honest with you, in the statistics world, nobody wants you to bring them anything that's less than 25. And 100 is really more of the standard, or the gold standard at least, but still 5 or whatever we're doing in the physical sciences, because people aren't trying to trick you. The science isn't trying to trick you in the physical science. There's not the variability of actual living organisms that move in time and stuff like that in general in physical sciences. So maybe we let ourselves off a little bit, and maybe we're wrong, I don't know, but maybe we let ourselves off a little bit by just saying 5's enough, and that's okay. But we're going to take at least 5 measurements of any quantity by repeating it. Okay. In the case of, let's say, measuring this guy, which I've done last time, you would measure, of course, like this. Let me unloosen that or loosen that. So you'd measure, say, this, if I call this the length, you'd measure that like that, get a reading. I'm reading this as 4.8. And then it looks like 4.8. I'll let you guys look too. Oh yeah, I don't have the camera on. No, I won't let you guys look. So you can see like this, but anyways, it's 4.8. And I technically don't have to read this as thoroughly because we're just doing an example, but I'm going to say this one's 4.834. Yeah, 4.834 is what I call this. And then I take it off. I move this around a bit and I put it on again. And now I'm reading 4.8. This one I got 3.8. Okay, so you see that it does actually change from measurement to measurement. And some of that might just me being erroneous and sort of sticking it across a different angle, but that's not erroneous if it's actually a different measurement at different angles. But I get at least 5 of those measurements, and I now need to know what number do I use. I've got 5 different numbers to use for that length or width or whatever I called it. So what the best number to use is to take the mean. So that's what we're going to do. Step 1, make a measurement. Make it again, make it again, make it again, make it again, make it 5 times at least. Then from there on out, you're going to use that figure's mean. In other words, you're going to add them all up and divide it by the number of times you did it. And that's going to be your best estimate of that value. Now, what are you going to do next? Well, you're going to take that first measurement and you're going to subtract it from the mean. Well, that might come out positive or negative. So let's square it just to keep straight. But now I've got units of centimeters squared, and that's not very helpful, but we'll take care of that later. Okay, now I'm going to take that next measurement and I'm going to take the mean and subtract it from the mean. And I'm going to square that. And I'm going to do the next measurement and square that, and do the next measurement, square that, and the next measurement and do that, square that. So I'm now up to the 5 differences squared. Now I'm going to divide that by 5, and that gives me the average square of the deviation. But again, we have units of centimeters. That's not very helpful. So we're going to take the square root of it, and that is the standard deviation. But it turns out the statistics don't work so well. In other words, that 68, 95, 99.8 number doesn't work that well if you actually divide it by 5. So it's better if you, in fact, divide it by 4. Okay, 5 minus 1. So instead, we're going to go back. We're going to take those sum of those deviations squared, and we're going to divide it by 4. And we're going to take the square root of that. And I now have the standard deviation. But that's not useful directly. It's only useful in the sense that I'm getting ready to do some math on it to make it useful to me. So now I'm going to take that standard deviation and I'm going to divide that by the square root of the number of trials, which in this case was 5. So I'm going to divide it by the square root of 5. And that's going to be my standard error. And I'm going to report that, assuming that is bigger or the same size as my instrumental error. I'm going to put that after the plus or minus when I tell people what the length of this polygon was, or what the length of this rectangular solid was. So the length of this rectangular solid was 5.348, say that was the mean. I would say the length of this rectangular solid is 5.348 plus or minus 0.005. Okay, whatever that standard error turned out to be, it'll be plus or minus that quantity. Now, if that quantity came up to be smaller than the instrumental error, which I estimated to be 0.001, then no, I have to use a 0.001. Okay, so that's our process with each individual measurement, is take a mean, and if you actually had different errors and different, maybe different labs are doing some of the data, so one lab might have a bigger error than another lab, then you'd really want to take the weighted mean, but we don't deal with that here, so you don't have to worry about it. But I'm just telling you, to be complete, if you have several people working on it and each person or each lab is known as having a different error than the other, or each person is known to have a different error than the others, then you take the weighted average, which means basically dividing the result by that small error gets a bigger quantity, and dividing that result by a bigger error results in a less weighty example. So that actually averages it out so that basically the people that have the lowest error are counted more frequently. So the weighted average is more the gold standard, but like I said, I very seldomly have to use that. I do use that occasionally with some plotting and of experimental evidence, because sometimes some of your measurements are so big you can't use a Vernier caliper, and then others are small enough where you can. So you have big error in the case of meter stick and a small error in the case of Vernier caliper. So anyways, that's how you get a particular number. Now you have a particular number, say a number for the width, a number for the height, another number for the length. With width, height, and length, you can use that to calculate volume. Notice I'm saying we're not measuring volume directly, so there's no instrumental error to consider. But what do? How does that error, what becomes of the plus or minus for the volume when you're doing that? And that's what propagation of error is about. And that's why I'm going to turn back on the document cam. So let me turn on the document cam real quick. And this is a fresh new pen, so I have to pull a little nipple off the end and everything. So it turns out in our case, we're talking volume is a function of width, length, and height. And I know this is exactly the example we did before, okay? But that's okay. It's just sort of a typical example that everybody can easily understand. And I'm just trying to make the process understood. And the formula for this is length, because that starts with a W, I guess. It's width, sorry, times length times height. Okay, that's the function V of W, L, and H. Okay, now what we know is, here's the symbol we use for error. So this symbol right here with some subscript is the error. And that error can be standard, or instrumental, or propagated. Okay, and inside this little circle is the variable measured. Oops, R first. Or the calculated value / function. So what I mean is, for instance, in this case, we're talking about a volume that is a function. So I'll say sigma sub V. And it turns out that sigma sub V, the formula for it is the square root of the sum of the squares. And I take the partial derivative of V with respect to W, and that's just the first one that came, times the error in W, and I multiply them and square them, plus the partial derivative of V with respect to L times the uncertainty in L, and I square them both. And then I take the partial derivative of V with respect to H times the error in H, and I square that. And that gives me what I get after the plus or minus when I report V. So for instance, I will report V of W, L, and H as equal to, so let's say this, for instance, let's say X is the best estimate of X. So when I put a bar over it, that's supposed to be the best estimate. So I'm going to say the best estimate of V is W average times L average, or best estimate, times H average, or best estimate. So why did I do that? I don't even know where that came from. So what I'm saying here is you're going to put the best estimate here or the average here. And in the cases where these are the things that I actually measured, this is where you put the weighted average or the average. In the cases where you're calculating, then this is just the best estimate. Okay. So what we would report now is V is equal to V bar plus or minus sigma V, where sigma V is found by that formula. There's another quantity that comes in handy, and that quantity is sigma V over V. And this is called the fractional error. And really the formula for it would be sigma F over F for any arbitrary F is actually the uncertainty in F, which could be the error, the standard error, whatever, or that sort of thing, divided by the best estimate of F. Okay, so that's how you go about calculating that. So just as a refresher, let's remind ourselves what sigma V over V, or what sigma V really is. So sigma V, remember, V is equal to length times width times height. So V is equal to length times width times height. I know I put that in a different order, but I don't care. The partial derivative of V with respect to, I said first was W. Well, that's just going to be L times H. The partial derivative of V with respect to L is just going to be W times H. And the partial derivative of V with respect to H is just going to be W times L. Okay, so that means the uncertainty in V is going to be equal to the square root of the sum. Okay, so the sum is going to be L H partial W squared plus W H, excuse me, I said partial, I meant error, L squared plus W L error L squared, which means square root best value of H, or excuse me, of L squared, best value of H squared, uncertainty in W squared, plus best value of W squared, best value of H squared, sigma L squared, plus best value of W squared, best value of L squared, sigma L squared. That's a really ugly formula. Okay, but it's right. It's 100% right. So if you stuck in all these values and squared them and added them up and took the square root like you're supposed to, that would give you exactly what goes after the plus or minus. And that's good. I mean, you get exactly the result you need. It would have the right units. You can tell the units are going to be length times width times the unit of length times the unit of height times the unit of width. Each of those squared, but you're taking the square root. So you're going to get centimeters times centimeters times centimeters, which is cubic centimeters. So that's great. But it turns out a much simpler formula can be gotten by doing this. You can say sigma V over V is actually just sigma V over length times width times height. I know I put them in yet another order. And I'm trying not to draw a vector, even though I did. Okay. So if I do that, what happens is I pull that W times L times H inside of the square root, and it becomes L squared times W squared times H squared, which originally I said W L squared H. So I'm going to say W squared, L squared, H squared, all in the bottom. That's from taking that. And remember that technically is the best estimate of W, L, and H, just like the time why I took the time to say that in this other formula. So L bar squared, H bar squared, sigma W squared plus W bar squared, H bar squared, sigma L squared plus W bar squared, L bar squared, sigma L squared. Now you can see where this pays off, because this guy and this guy cancels out with this one and this one. This guy and this guy cancels out with this one and this one. And this guy and this guy cancels out with this one and this one. So you see, when you cancel out the L and the H, all you get is W. So we get the fractional uncertainty in W squared plus the fractional uncertainty in L squared plus the fractional uncertainty in, that was supposed to be an H down here. Nobody caught me. Fractional uncertainty in H squared. And that's actually how you actually would work that out. You take sigma W over W, put that in here, sigma L over L, put that in here, sigma H over H, put that in here. Notice that's just the uncertainty divided by the best estimate. And it turns out for any function f of x, y, z, w, l, q, whatever, for any number of variables, this is always the formula, wait a second, equals x times y times z times w times l times q times, or excuse me, times dot, dot, dot. It always turns out that the fractional uncertainty for a product is equal to the sum of the fractional uncertainties. So sigma x over x squared plus sigma y over y squared plus sigma z over z squared plus sigma w over w squared plus sigma l over l squared plus sigma q over q squared plus dot, dot, dot. Okay. So that turns out to be the case for all functions that are just products. So for instance, x times y times z, or x times y times w times z, or x times y times z times w times l times q times x1 times x2 times x, any product like that. It turns out also it's the same for f of x, y, z, w, l, q, dot, 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 for that equaling x, w, l, q over x, or excuse me, over y, Z, any orders of that also gives the same formula. Okay, so if you do division in any order whatsoever, with any part on the top and any part on the bottom, you still get the same fractional error. Of course, you might wonder, well, once I've got the fractional error, I've got this stupid thing that's in a percent or in decimal, but it has no units. How is that any help to me? Well, it's very helpful to you, because now all you have to do is say that V, which is equal to V bar plus or minus sigma V, is actually equal to V bar plus or minus fractional error of V times V bar. And then, so all you have to do is take the number you got from this calculation and multiply it by your best estimate of V, and you're done. Okay. So here's what I want you guys to do now that I've rehashed all that and helped you understand all that stuff. I want you to do a few functions, and I'm going to post some photographs up here. The photographs will be posted. The mail is running really, really slow because they're big files. So I'll post them by the end of the day. And then I'll write in an assignment link where you're going to turn this in, and I'll tell exactly which things you have to do there. So it'll get a better explanation, but this is all you have to do for lab this week. Is I want you to take f of it. All right, let's say f is equal to 2x plus 3y. And I want you to tell me what sigma f is. And I want you to say, what is sigma f over f? Make it as neat as you can. Try to get it smooth, but if it doesn't turn out neat, that's okay. It's just going to have to. It just, the math is what the math is. It is what it is, right? So I want you to do that for f of x. Our f equals, let's say, x squared plus y squared plus z squared. I want you to tell me sigma f and sigma f over f. I want you to take f equals x squared plus x plus 3 and tell me what sigma f is. Sigma f over f. I want you to take f equals, let's say, a x squared plus bx plus c. In other words, quadratic. Sigma f over f. And let's say f is equal to m times v times cosine theta. So your variables are m, v, and theta. I want to know sigma f over f. And I want to know f is equal to m v sine theta. Everybody follow what we're doing now? Okay, and let's say b is a function of I and r and is equal to mu 0 I over 2 pi r. I would like to know sigma b and sigma b over b. And that's it for those. I think you all should be able to record that from here. I will either take a photograph of this or type it all out and put it in the description for this week's lab where you're going to actually turn it in. This can be done and should probably be done by hand. Y'all are welcome to LaTeX it, but I don't need you wasting all that time. So don't do it if it wastes time for you. but I want you to do all that. And I want you to read, why did I write B there? I don't know. Read Vernier measurements. And record with photo names. So you didn't see this here because I was writing it like that, but I will post photos up there with names with no answers. I'm also going to put photos up there with names with the answer built into it. And in those cases, that's to give you practice. But in this case, where it doesn't have the name, it'll be like photo 1, photo 2, photo 3. I want you to actually read the measurements, zoom into the picture as needed. It'll be sometimes multiple pictures for the same one. So it'll say like P1, P2, P3. Okay. So you're going to turn all that in. You can, like I said, do it all by handwriting, and you can just take a photograph and turn that photograph back into a PDF, or you can paste it into a Word document and then turn that into a PDF. Whatever you want is fine. Just make sure it's big enough where I can read it, and make sure you write it neat enough where I can read it. Other than that, you're good to go. Okay. Does anybody have any questions on that? Okay, well, that's lab for today, and I think this will give you plenty of opportunity. I mean, if you wanted some more practice on this stuff, you could, take anything you wanted as far as measurements go, and do means and standard errors and standard deviations and all that good stuff. But once you've done that, one time by hand, you sort of understand the process, and you should probably pretty well understand how to do it from there on out. And you don't have to do it by hand anymore, because your calculator does a lot of those calculations for you automatically. It doesn't mean it does a standard deviation as a bare minimum, and then you just take the standard deviation and divide it by the square root of n, and you're good to go. So you have a good one, guys. I will see you again at 2 o'clock. I will wait here until the last person leaves in case anybody has any questions, and that can be questions from lecture, our lab, our midterms, or anything. Ryan or Zachary, do you have any questions?
No, just making sure I wrote down everything. So yeah, so that optics lab is posted.
Yeah, I finally posted it today. It's funny, I made it, the day you told me, which was what, Wednesday of last week, I think, or it might have been Monday of last week, and it just sat there unpublished. But
Okay, I go post that now. Thank you so much.
no problem.
Is this a lot like the last error propagation we did?
Yeah, the difference is you don't have to do all those statistical calculations, and you don't have to do all the proofs. I did one of them for you, for instance, but now your job is to do these 7 error propagation calculations, and then to read these Vernier calipers. These kind of questions, now that I've made them more concrete, there's a good chance I might have photographs of Vernier readings on your final exam, for instance, and there might be
I see.
error. Yeah, there might be propagation of error problems on your final exam now.
Okay. All right. Thank you.
No problem. All right, I'm out of here, Ryan. Unless you need me anymore.
No, I'll see you at 2.
All right, see you too, bud. Bye-bye.